For millennia, we gazed at the stars, wondering what lies beyond. Today, that wonder is answered. NASA has unveiled the first ever high-resolution image of Proxima b, orbiting our closest stellar neighbor, Proxima Centauri. This is not a simulation or an artist's rendering. This is a direct photograph, a cosmic postcard from just over 4 light-years away. The image marks a monumental leap, transforming a faint, indirect signal into a tangible world we can now study and debate. We have officially entered a new era of exoplanetary science. Before today, Proxima b was a world of data points and probabilities. Now it's a world of texture and color. This achievement is the result of decades of scientific ambition and technological innovation. The journey to capture this image pushed the limits of optics, data processing, and physics. Isolating Proxima b's faint light from its star is an engineering marvel, a testament to human ingenuity. As we examine this photograph, we see not just a distant planet, but a reflection of our own progress. Every pixel tells a story, not just of Proxima b, but of our journey to understand the cosmos. This image is more than data. It's an inspiration, a call to the next generation of explorers. To grasp the magnitude of this image, we must understand Proxima b. Discovered in 2016, Proxima b is our closest known exoplanet, orbiting Proxima Centauri just 4.24 light-years away. It's a rocky planet, at least 1.17 times Earth's mass, possibly with a solid surface. Its orbit is extreme, just 4.6 million miles from its star, completing a year in 11.2 Earth days. Proxima b is likely tidally locked, with one side in perpetual daylight and the other in endless night. Its location in the habitable zone raises hopes for liquid water, but Proxima Centauri's violent flares could threaten any atmosphere. This cosmic tug-of-war between warmth and radiation makes Proxima b a scientific mystery. Until now, our knowledge was built on indirect detection, wobbles and dimming. We wondered, is it a barren rock, a water world, or something else? Now, with a photograph in hand, speculation gives way to observation. We can finally begin to truly know our nearest neighbor. The era of guessing is over. The era of discovery has begun. Capturing a direct image of Proxima b is one of astronomy's greatest challenges. The planet's faint light is overwhelmed by its star, like a firefly beside a searchlight. Astronomers use coronagraphs, tiny masks inside telescopes, to block starlight and reveal the planet. Even then, stray light and diffraction make detection incredibly delicate, requiring nanometer precision. The next hurdle: resolution. Proxima b's separation from its star is minuscule from Earth's perspective. No single telescope is large enough, so astronomers turn to interferometry, combining light from multiple telescopes to simulate a giant virtual eye. This technique achieves the sharpness needed to distinguish planet from star. Photographing Proxima b meant pushing interferometry to its limits, linking telescopes across continents. Only through this global effort could we finally see our distant neighbor. The image of Proxima b was captured by the Hyperion Stellar Imager Array, a global network of 24 8-meter telescopes. Strategically placed from Chile to Tibet, the Hyperion Array operates as a planet-wide optical interferometer. Its core by quantum optical interferometry, using quantum entanglement to link telescopes and reconstruct light as if from an Earth-sized eye. Data from each telescope is transmitted to a central quantum computer, which processes the signals with unprecedented precision. Project Blue Dot, the observation campaign, involved 1,200 hours of exposure and yottabytes of data. An AI-driven adaptive optics system counteracted atmospheric turbulence in real time. The final image is a composite, stitched from thousands of exposures, with an angular resolution sharp enough to reveal continent-sized features. The Hyperion Array is more than a telescope. It's a new tool for exploring dozens of nearby star systems. This achievement marks the dawn of a golden age in exoplanetary imaging. We now have the means to see other worlds as never before. The released image is a marvel. Proxima b appears as a resolved sphere, its tidally locked nature on full display. The day side is brightly illuminated, showing mottled regions of varying color and brightness. Darker, reddish-brown patches may be volcanic plains or exposed rock, while brighter, bluish areas could be water ice or shallow oceans. The terminator, the boundary between day and night, is a diffuse, hazy zone, possibly home to clouds or fog. This twilight region may offer temperate conditions, making it a prime candidate for habitability. The night side isn't pitch black. A faint, ruddy glow suggests heat transfer, likely through an atmosphere or oceanic currents. This thermal emission hints at a dynamic world, not a frozen, inert rock. The image provides the first visual evidence of complex planetary processes at work. Proxima b is no longer just a data point, it's a world with character. The subtle halo around Proxima b's limb excites atmospheric scientists. Using direct imaging and transit spectroscopy, researchers detected water vapor, a landmark finding. Carbon dioxide and tentative methane signals add intrigue, as these gases can be linked to both geological and biological activity. The presence of a substantial atmosphere is clear, not a thin veil, but a robust envelope. The hazy terminator likely hosts clouds, matching models that predict a ring of clouds on tidally locked worlds. The atmospheric haze's pale blue tint suggests Rayleigh scattering, implying a thick, possibly nitrogen-rich atmosphere. Proxima Centauri's flares threaten atmospheric loss, yet Proxima b seems to have retained its air, hinting at a protective magnetic field. While we can't yet detect that field, the atmosphere's survival is a clue. These findings drive the case for future missions to probe exoplanet magnetospheres. For now, Proxima b's atmosphere is a beacon for further exploration. The image opens a new chapter in comparative planetology, revealing Proxima b's geologically diverse surface. Reddish-brown regions may be ancient volcanic plains rich in iron and magnesium. A massive, dark structure, the Great Caldera, could be a colossal shield volcano, fueled by constant stellar heat. Brighter, bluish basins might be filled with water ice or briny oceans, their composition still uncertain. Extreme radiation would boil pure water, but salty or exotic frosts could persist. Tidal locking likely shapes unique tectonic features, rift valleys or compression ridges, along the day-night boundary. The image isn't sharp enough to resolve these yet, but it guides geologists' models. Proxima b's geology is unlike anything in our solar system. We're just beginning to decipher its alien landscape. With a substantial atmosphere and hints of water, Proxima b's habitability is now a tangible question. The image reveals key ingredients for life: a solid surface, energy, atmosphere, and possible liquid water. Life here would need to be resilient, perhaps underground or in deep oceans, shielded from radiation. The twilight zone with moderate temperatures is the most promising habitat. Methane alongside water vapor and CO2 is tantalizing, but its origin, biological or geological, remains unknown. This image refines the Drake equation, showing that habitable worlds can exist around red dwarfs. Proxima b is our first close-up, but it hints at countless other possibilities. The first high-resolution image of Proxima b is a watershed moment, transforming a point of light into a world. We see a dynamic planet with atmosphere, clouds, and surface features hinting at water and geology. The Hyperion Array's data answers old questions and sparks new ones, setting the agenda for future research. This is a triumph of global collaboration and human curiosity. The image is a symbol of our collective potential, inspiring a new generation to look to the stars. Next steps, deeper observations, sharper images, and perhaps even space-based interferometers. We stand at the dawn of a new age. Our nearest neighbor is no longer a mystery. The journey has just begun. What will it take to one day set foot on that distant world?